Let us briefly review what we have done last time in the last lecture. We were trying to derive a method for finding the root of an equation f(x) is equal to 0. f(x) could be algebraic equation, it's an algebraic equation, so it is a transcendental or a polynomial equation. What we discussed last time was that in the neighborhood of the exact root we shall approximate the curve by straight line. So it is a valid justification because in the neighborhood of this exact root the curve can be approximated by a straight line, that this straight line is f(x) is equal to a naught x plus a1 is equal to 0, and we said that the different methods can be derived by trying to derive the values of a naught and a naught in a different way. Now if I solve this particular equation, what I would get is x is simply equal to minus a1 upon a naught. Now the first method that we were derived last time was the secant or the chord method. We have taken two approximations xk minus 1 xk to the root. There are any two approximations, as we said the root it is not necessary that the root should lie between these two approximations. So these are two arbitrary approximations near the root. Then we take the point on the curve. So we have f of x minus k minus 1 is fk minus 1, f of xk is fk. Now this point should lie on the given straight line, therefore it should satisfy the two equations, these two equations that we have derived. Now there are two equations for two unknowns a naught and a1. So I solve these two equations for a naught and a1, and we have then produced the values of a naught and a1 as follows. We have just subtracted the two equations and produced the value of a naught. Then from the first equation we have produced a1 is equal to a naught. Therefore since the solution of this equation is simply x is equal to minus a1 upon a naught, we have then written the next approximation as xk plus 1 is minus a1 upon a naught. We substitute the values of a1 and a naught that we have got over here, and I have written the a1 in terms of a naught, so that division by a naught is easy here, cancellation is easy. So I write this as xk minus fk upon a naught. I substitute the value of a naught that we have got in the previous slide. So if I substitute it and simplify, this is what we have done last time. Now here this cancels and I can write this particular form. We also said that in one of these two forms, either of these two can be used. For computational purposes 3 is useful for us because it is simple, whereas for error analysis we would like to use the form of 2, which we shall see why it is convenient for error analysis. We call this as secant method. Now I would briefly tell you also why we call it a secant method, what is its geometrical representation before we make some comments. Now we mentioned earlier that xk minus 1 and xk are any two approximations to the root. The root need not lie in this particular these two values. The reason is the method gives convergence to the root from one side of the root. That means we have seen the graph of the we have seen here that this is the root. Now I take any two approximations on one side and these two approximations will converge to the root from this side or from this side. Now what happens is if you by chance you take, because you may not know it, if we take the root lying between xk minus 1 and xk, it would take one or two iterations to go to one side of the root. So it will go either to the right or left of the root and then start converging. So we may lose one or two iterations before this actual procedure starts. Now it is necessary to compare all the methods. The correct way of comparing these two methods are the cost of evaluation of the function. There are other costs are very trivial, because if you look at this method I can say that there are two multiplications here, one division here and two subtractions here. So it is very trivial because the number of total operations are simply 5 operations, which would not take even few microseconds. So the cost of the computation of this is trivial, therefore the only cost that will be expensive would be the evaluation of f(x), which we expect it to be a very complicated function. Therefore we shall say that the cost of this is evaluating one function, that is f of xk plus 1 at each iteration. Now the computation of this, I mean it is very easy to remember how this right hand side could be written next approximation. If you look at the 2 points, now if you look at the 2 points that we have here, xk minus 1 fk, forget about these signs I will explain it to you. The point on the curve is xk minus 1 fk minus 1 xk and fk. Now if you look at the numerator of this is nothing but the product of these two, this abscissa, this ordinate minus this. So this sign represents that we are taking the plus sign for this product, and this sign represents that this is we are taking the minus sign for this product, and the denominator is just the difference between the ordinates, that is these two ordinates difference between this. So it is very easy to write down the secant method as the product of these two minus product of these two and subtract these two ordinates.
But sir, you said only fx of k plus 1 is need to be calculated here.
At any no, this is the already two approximations are available, 2 values fk minus 1 fk is available. Now this computation will give me fxk plus 1. Now when I go to the next iteration, what I would then need would be, I would need this next point xk plus 1 fk plus 1. Now that means I have to compute fk plus 1 to go to the next iteration. These two are available. Now when I go to the next iteration, these two are available to me. Now I go to the next iteration. So at each iteration we will be evaluating one extra function. Now there is a very interesting graphical representation for this. It gives you the intersection of the chord passing through the points this xk minus 1 fk minus 1 xk fk with the x axis is the next approximation. The reason is, when we approximated by straight line in the neighborhood of the root, we are taking the next approximation as the point of intersection of that line with the x axis. So what we have really done here is, we have taken this point xk minus 1 fk minus 1 on the curve, xk fk on the curve, join these two points by straight line, let that straight line intersect the x axis at a point, and that point will be our next approximation. Now how does this look like? Now I have drawn this particular thing again here. I have taken a point x0. So x0 f0 is a point on the curve. This is another approximation x1. x1 fx1 is another point. Now according to this, I must join these 2 points on the graph, that is x0 f0 x1 f1, join this, and this straight line intersects the x axis at x2. Now I find the point x2, that is one evaluation fx2, then I join the point x1 fx1 x2 fx2. Now it goes in a sequence, we are not testing whether the root lying or anything, we are just going in a sequence, that is all. Then x1 fx1 x2 fx2, we join these two, draw a line, and we will cut at x3. Now I take fx3, I join the point x2 fx2 x3 fx3 and so on. So the convergence will be going from this side to this particular root. So that is the what's known as the secant method, or simply the chord method. And as you can see here, the convergence to the root is from one side. If the graph was different, the convergence would be on the other side. So we do not know from which, because we do not exactly know how the graph is for a particular function, we do not know from which side it is going to converge. Now we can modify this secant method, and very minor modification we make, and then we shall call this as a regular falsy method, that is called regular false position method. And in this method what we do is, in the secant method we said that the root need not lie between any approximation xk minus 1 xk, but in regular falsy we will force that the root should always be within the particular interval. So if I start with xk minus 1 xk, xi must lie between xk minus 1 xk. Then what I will have to do, I will compute my f of xk plus 1. So I compute my f xk plus 1, and depending on the sign of f of x plus 1, I will now decide whether the root lies between xk minus 1 xk plus 1 or xk plus 1. Suppose the root is lying between 1 and 2. Now I produced the new value as 1.8. Now I will decide whether root lies between 1 and 1.8 or 1.8 and 2. Then I will proceed with the secant method further, and then every time before I go next iteration, I will test whether the root is in the given interval or not. So, the only disadvantage, I mean here we are making sure that we will always converge, but the disadvantage is one end of the interval, that means we starting interval initial approximation x naught x 1 we started, one of the end points of this interval is always fixed and convergence to the root is obtained from other end. So, what we are stating is if you start with x naught x 1, root is between this, either x naught will be fixed and x 1 will move towards the root, or x 1 will be fixed and this will move towards the root. And this is disadvantage because suppose you start with the length of the interval is large, let us say the interval is lying between 1 and 3 you started, then either 1 is fixed, suppose the root is 2.2. So, 1 is fixed and the root converge, this for the approximation or the number of iterations it will take will be much more, and the accuracy, the order of the method will also drop down because one endpoint is always fixed. Now, let me just illustrate it by graphically what this really means, how it is happening. Let us take the point x naught and x 1 in which the exact root lies, x naught f x naught, x 1 f x 1, I join this straight line, I got the point of intersection x 2 as my new approximation. I determine f x 2 and take the point x 2 f x 2. Then the root lies between x naught and x 2. Since the root lies between x naught and x 2, I now throw away the interval x 2 to x 1. Now I consider x 0 f x 0, x 2 f x 2. Now I join these 2 points again. It will now intersect at x 3. Again I test whether the root lies between x naught x 3 or x 3 x 2. Root lies in x naught x 3. Therefore, I now consider x 3 f x 3, then join the line x 0 f 0, x 3 f x 3, next will be iteration. Now, you can see in this iteration process this end point x 0 f 0 is always fixed, it is only the other approximation is moving towards this. This is what we meant by saying the disadvantage of the regular falsi method, that the one end of the approximation is always fixed. Therefore, if you want a good accuracy in regular falsi, we must have a sufficiently small interval so that the accuracy achieved is high. Otherwise, it is going to take lots of iterations in order to have the convergence, because in fact we are going to show in a later lecture the convergence rate of regular falsi method is lower than the secant method. So, what we really was saying is that if both the methods converge, secant method is going to be faster than regular falsi method, and we know the reason why it is happening, but we will be able to show mathematically that the secant method is going to be faster than the regular falsi method. Now, let us take a simple example. Let us take the equation f x is equal to x cubed minus 5x plus 1. Now, this example we have tested it earlier. We can show that f of 0 is 1. I can just write down what is the values of f of 0 here. F of 0 is equal to 1 here, and f of 1 I can substitute 1 here, and this gives you minus 3. So, I know the f 0 f 1 is of opposite sign, therefore, the root lies between 0 and 1. Now, the example is that perform 4 iterations of the secant and regular falsi methods with initial approximations to the root taken as 0 and 1. So, that is the interval in which the root lies. Now, we compute first f of 0, that is 1, compute f of 1, that is minus 3. Now, to just illustrate it, now we have the value, the x 0 is the abscissa, the value of the ordinate is 1, then we have the abscissa is 1, ordinate is minus 3. Therefore, the next iteration would be the product of these two, 0 into minus 3 minus 1, that is numerator, and the difference between the ordinates minus 3 minus 1. So, the denominator is minus 4. So, we take this product with a positive sign, this product with a negative sign, and then I find the ratio of this, that is 0.25 is my next approximation. Now, I determine f of x 2, that is f of 0.25. I evaluate it, substitute in the given polynomial, and I get this value. So, what I now have, the next value is 0.25 as the abscissa, and I have the ordinate as minus 2.234375. Now by proceeding forward I multiply these two with a keep a positive sign, multiply these two and multiply by negative sign, and then divide by these two ordinates. So I can now produce the next value x3 as this value minus this is equal to this. Now I compute f of x3, that is the whatever we have given the polynomial as x cubed minus 5x plus 1. Then I compute the next iterations, I have just given it to you, I have not written these details. X4 comes out to be 0.201736, x5 is 0.201640. Indeed this is accurate to all the decimal places, we will see later on. So the application of the secant method is very simple. I mean the amount of computation or the computed time that would take will be hardly few seconds, not even few seconds, depending on the problem, because as we have seen, the number of operations that we involve, major operations are only 3, 2 multiplication, 1 division, and 2 minor operations of addition, and only 1 function evaluation. Therefore even if you do 100 iterations, you won't even cross a second even for computing a particular root. Now let us do the same thing by regular falsy method. So we started with x0 is 0, x1 is 1. So the first step is the same, that is your evaluation of the first one. The first step will be the identically same because this will be the same. So I would therefore have x2 is 0.25, f2 is minus 234375. Now I will determine whether the root lies between 0 and 0.25 or it lies between 0.25 and 1. I find f0 f2 is negative, therefore the root should lie between 0 and 0.25. When once I decide that the root lies between these two, in actual computation if you are writing a program for this one, you will initialize the right hand side as 0.25. You started with AB as or x0 x1, and if you take it, then right hand side is initialized as the new point, so that the same formula can be repeatedly used. You can put it in loop and then come back and then do it. So you can reinitialize this as the new value. If the left hand side is changing, you will change accordingly the left one, so that the same formula is written in the program. So now I compute x3 with these two values. That means now what I am taking here is 0, 1, and I am taking 0.25 and minus 0.234375. So now you can see the secant method and this the difference. In secant method we are taking one after the other in sequence, x0, x1, x2, x3, there is no testing. Here everything will change depending on where the root lies. Therefore the root lies between 0 and 0.25, therefore this. Now you can guess one thing here, that this right hand side has moved, left hand side is fixed. So in all our future iteration 0 will always be retained. Now you can see x3 compute 202532, f3 is minus 0.043252, that is the value of f3. Now again f0 f3 is negative, therefore the root lies between these two values. Now I have given the next values as x4 as this and x5 as this, and we have seen that the end point 0, the left end point 0 is always fixed. Now we have now derived the secant method and a variation to it, so that the method if converges, secant method converges faster than the regular falsy. Now in many problems this convergence may not be sufficient for us, that means it is not converging sufficiently faster for us in a particular problem. So we would like to have some methods which converge faster than the secant method. One method is called the Newton-Raphson method. In deriving the Newton-Raphson method, in literature you will be surprised that Newton-Raphson method is also today one of the most powerful methods for finding a root of the equation. We will see later on a multiple root of the equation or a system of nonlinear algebraic equations. This method can be adopted to that one. So we will see why it is so. Even though higher order methods available, we still prefer this because of some reason. We assume that the derivative of f dash x can be obtained. So that means given fx, and will differentiate it and get f dash x. Then I will use f x and f dash x to find the straight line. We are still doing the approximation by straight line. So, I will try to evaluate a naught and a 1 that is there in the equation of straight line by using the data of f x and f dash x. Therefore, I need one approximation only for using the Newton-Raphson method. Let x naught or x k be any first approximation. If x k is the approximation, I substitute in given polynomial approximation, that is your linear polynomial. F k is a naught x k plus a 1. Now, I differentiate a naught x plus a 1, derivative is simply a naught. Therefore, f dash at x k is going to be constant, that is a naught. Therefore, a naught is found, a naught is f prime of k. Then I can find a 1 from the first equation as f k minus a naught f x k. So, because the equation we have approximated by straight line, its derivative is only a constant. Therefore, derivative at that point wherever the approximation is simply a naught. Now, the value of x is next approximation is minus a 1 upon a naught. So, I would therefore write x k plus 1 is minus a 1 upon a naught. A 1 we have just now derived, a 1 a naught x k minus f k by a naught. I taken this minus sign inside, divide it out, I will have x k minus f k upon f dash k, that is k is equal to 0, 1, 2 onwards. Now, before we make a comment on the application of this, let us see how this is same as the saying that we are now approximating by straight line in the neighborhood of the exact root. Now, what we are doing in the Newton-Raphson method is we are taking the point x k f k on the curve, we write down the equation of the tangent at this point to the curve, take the point of intersection of the tangent to the curve with x axis as our next approximation. So, I take the point x 0 starting approximation, x 0 f 0 is my point on the curve, then I draw the tangent to the curve at this point. Now, this line meets the x axis at x 1, this is my new approximation. Now, I take the point on the curve x 1 f x 1, I draw again the tangent at this particular point, this tangent cuts the axis at x 2. Now, this is my next approximation. So, I continue on and then approach the root xi here. This is the graphical representation of the Newton-Raphson method. Now, you can see of course that the root is converging from one side, but it has got better properties. Let us see what are these better properties. Now, first of all, the computational cost. The computational cost has increased compared to secant method. We have to evaluate one function and one derivative. Given a x k, we need f of x k and f prime at x k. So, the cost of evaluation has gone up by one function and this, but we shall show later that the Newton-Raphson method, the rate of convergence is higher, much higher than the secant regular falsy methods. Therefore, since we get faster convergence for this, we do not mind if the Newton-Raphson method take 10 iterations, and whereas secant method has taken say 15 iterations. So, if you are talking about the cost, secant method will be taking 15 function evaluations, but this has taken 10 iterations, but the total evaluations are 20, but the number of iterations that you will be taking will be much less. So, that the total cost that we are computing when you get the final answer would be much less for the Newton-Raphson method than for the secant or the regular falsy methods. Now, let us repeat the example that we have just now done it. So, find the real root of the equation x cubed minus 5x plus 1 is 0, the same example, but I am starting with giving an initial approximation as 0.5 using 3 iterations of the Newton-Raphson method. Now, here the idea is when once you have found out the interval in which the root lies, we arbitrarily take any point in this interval as our starting approximation. In fact, an idea will be given when you write down say f of 0, let us say it is lying between 1 and 4, f of 1 and f of 4 is known. Which one is closer to 0 will be that particular point. Suppose the value of the f at 1 is, so let us say minus 0.5, f at 4 is plus 1.5. The root lies between this, but 1 is closer to 0. Therefore, I will take a value closer to 1 as my initial approximation. So that will reduce the number of iterations. And second most important thing that happens here is, as I have just shown in the slide, the convergence of Newton-Raphson method is also from one side of the root. Therefore, if suppose you may ask what would happen if instead of taking in the example I have just now said, instead of taking 1.2 as your starting approximation, you take 3.8 as the approximations. Then since it is to converge from this, sometimes Newton-Raphson method goes around that root once or twice, then start converging from here. It depends therefore on how properly you chose an initial approximation, and the convergence will be obtained. But however, if the number of iterations is being taken is 50, you may not mind to lose 3-4 iterations in the beginning, so that it will adjust to the value to come to the one side and then start converging. So here I need to evaluate two quantities, that is our fx and f dash x. Fx is x cubed minus 5x plus 1, I differentiate it, so 3x square minus 5. Then I will first of all construct my Newton-Raphson method, what the method is. The method will be xk plus 1 is xk minus f of xk, that is evaluation of fx at xk, derivative in the denominator 3 times xk square minus 5. So this is my basic iteration method, Newton-Raphson method, from which I will substitute the successive values and then get the next iteration onwards. For in the problem we are given, you start with the approximation x naught is 0.5. So we will substitute x is equal to 0.5 in this and write x1 is equal to x naught minus x0 whole cube minus 5 times x naught plus 1 by 3 times x naught square minus 5, and we simplify this and get 0.176471. Now I use this value of x1 to compute the next approximation from here for k is equal to 1. When k is 1, I have x2 is equal to x1 minus x1 cubed minus 5x1 plus 1 by 3x1 square minus 5. Now I compute this by using this x1 and I produce this value, and I have not written the third iteration, the steps, but the third iteration value is 201640, which is the same value which you obtained in the two other cases, but with 5 iterations which we have obtained over. We can derive it in alternative way, which helps us also to construct still higher order method than the Newton-Raphson method. Now at the moment I may state, we will prove it in this lecture or next lecture, that Newton-Raphson method has got what is known as second order convergence, whereas the regular-Falsy method has got order of convergence 1. Secant method has got not an integer, it is a fraction, it is 1.618 as the order of convergence. What does this order of convergence really mean? We will explain it later again, but let me just say that it connects the errors at the present step to the previous iteration. So that means error at xk is connected to error at xk plus 1, how the error is changing. If the order of convergence is quadratic, the error in the present step will be the square of the error at the previous step. Suppose in the previous step you were at an error of 0.1, you can surely say that my present result is 0.1 whole square accurate, that means 0.01 10 to the power minus 2 accurate. Next iteration 10 to the power minus 2 whole square, so 10 to the power minus 4 accurate. So the convergence will be very fast, and that is quadratic convergence. Whereas if I take the regular-Falsy, the order is 1. If the error is 0.1, I would expect only one decimal place to get. So in the next case it is again order 1, so it will get only one decimal place, whereas Newton-Raphson method is jumping by square of the error in the previous case, and we would expect the error to be less than 1 in any case. So if the error is greater than 1, you may say it is meaningless, but yes, it is meaningless, because but the error means we are closer to the root, therefore it is less than in magnitude 1, therefore the error would always be smaller than 1, therefore we are talking of square or cube or so. Now I would like to have a derivation, alternate derivation for Newton-Raphson method, which would help us to construct a still higher order method than Newton-Raphson method. Now let us take xk as approximation to the root xi. Now if I add the quantity h, the correct quantity, I can get the exact root, that means xk plus h is equal to xi, that is my exact value. Since xi is exact, f of xi must be 0. By definition f of x is 0, x is equal to exact solution, xi is the exact solution, therefore f at xi should be 0, that is f xk plus h. Now just open it up by Taylor series, write down the Taylor series and retain only first term. So f of xk, h times f prime at xk plus order of h square terms, the higher order terms, order of h square terms. Then to derive Newton-Raphson method, we simply drop the second or higher order terms, we drop the order of h square terms. That means I set them all of them 0, I neglect these higher order terms. If I neglect the higher order terms, what is left out for you is f of xk plus h times f prime of xk only. Now if I neglect these higher order terms, what I would get is f of xk plus h times f xk is equal to 0. I solve for h. Now this is an approximation, h is equal to minus f of xk by f dash of xk, but mind you h is here an exact value, but here we have now approximated in this, therefore whatever I got here is not exact h but an approximate h. Now the new approximation therefore will be xk plus h is the new approximation, because this what I have got here is not the exact value of h. So what I am getting here is not the exact xi but an approximate xi. So the next approximation will be, I will put it here, xk plus 1 is equal to xk plus h, therefore xk minus f of k minus f dash k. Therefore simple Taylor series would give me the alternative method of deriving the Newton-Raphson method. Of course we just make a comment here that if the initial approximation is far away from the root, then the iterations may diverge. For example, the root lies at minus 10. If I start the approximation on the positive side with plus 5, the root is 15 units away. Therefore we may not expect the Newton-Raphson method or the secant method to converge at all. Therefore the approximation, initial approximation should be closer to the root, and that will be obtained of course by using the initial value, the theorem that we have given, the intermediate value theorem. We can use the intermediate value theorem and get the root. Now let us go to the methods which I can construct superior to Newton-Raphson or the secant method, which I would call them as iteration methods based on second degree equation for the solution of f(x) is equal to 0. Now in the earlier discussion we said that in the neighborhood of the root I can approximate the curve by a straight line and then obtain the methods, but now I would say I would like to take a better approximation than a straight line. The better approximation than a straight line is a parabola passing through 3 points, which is nothing but a second degree equation. So instead of approximating by a linear polynomial, I will approximate x by a quadratic polynomial which will be a parabola, that is a second degree equation. Now to get higher order approximation than this, we approximate the curve in the neighborhood of the exact root by parabola, which is a second degree equation. So I will take the second degree equation as a naught x square plus a1x plus a2, where of course a naught is not equal to 0, otherwise it is going to be linear polynomial, and these 3 parameters are to be determined. Now again the way in which you determine these 3 parameters a naught, a1, a2 would design a new method, and which we will call by different names. Now the first method is called the Chebyshev method. Now in logic the Chebyshev method is simply this: the alternative derivation of Newton-Raphson method we are given using the Taylor series. What Chebyshev method says is, instead of taking order of h square neglecting, use order of h square terms also, but neglect order of h cube. Keeping the second order terms would imply that we are approximating the curve in the neighborhood of the root by a quadratic curve, that means a second order polynomial approximation. I am deriving it here in a different way, the values of a0, a1, a2 different way. We start with only approximation xk. Now when we have derived the Newton-Raphson method, we said let us assume that f derivative exists and evaluating f dash xk. Now in Chebyshev method we say let one more derivative exist, that means second derivative also exists, that is f, f prime, f double prime. So we will use the three values f, f prime and f double prime. So fk is a0 xk square plus a1 xk plus a2. I differentiate the given approximation. I will get here 2 times a0 x plus a1. So at the point xk I will get f prime at xk 2 times a0 xk plus a1. Differentiated once more, I simply get 2 times a0. So the second derivative at xk is 2 times a0. Therefore this gives us 3 equations in which we can find the solution of a0, a1, a2 in the backward direction. The last value, last equation gives us a0 is half of f double prime at k. a0 is determined. Substitute in the previous equation, I will get a1 is equal to f prime of k minus twice a0 xk. So I bring it to this side. Then the a0 is f prime k, f double prime k by 2. I substitute it here. So a1 is simply f prime of k minus xk f double prime of k. Now I will use these two values of a0 and a1 over here and find my a0 from here. So what we have done here is I have taken a0 from here, this is fk minus a0 xk square and this is minus a1 of xk. I substitute the value of a0, that is f double prime k by 2, and I substitute the value of a1, that is f prime k minus xk f double prime k, and this minus xk is multiplying it. Now here you can see that this both are second derivatives, so they simplify and we have fk here and this a minus xk f prime k, and this gives me plus half xk square f double k. Now I have determined the values of a0, a1, a2, and what I will have to do here is I have to go back and substitute. Let me just put this one, I go back and substitute a0, a1, a2 over here, the values that we have substituted here. So if I substitute it back, I leave little bit of algebra is there to simplify it. I collect all the terms, then that can be simply be put in the form of substituting. I simply collect the terms of f prime k and f double prime k, and if I collect it, it just comes out like this. These terms they all combine, fk plus x minus xk f prime k plus half x minus xk whole square f double dash k is equal to 0. Now here we have to make a decision now. Now this is a quadratic equation, therefore it will cut the x axis at 2 points. Only one of the points is our root, the other point is not a root. Therefore we have to throw away one of the roots and then take one of the root as our approximation. Which one is that one, we will have to determine from here. Therefore out of these two roots, we will now, to find the next approximation, we will use a further approximation inside this, so that we are definitely towards the root. And what it is, let me just say. To make the comment that I made earlier, that if I had written the Taylor series alternative derivation of Newton-Raphson method, I have neglected order of h square terms and got my Newton-Raphson method. Now if I retain the order of h square terms, then I would get the Chebyshev method. Now you can see this is nothing but the Taylor expansion of f xk plus h, and h is xk x minus xk. So this is fk plus h f prime k plus h square by 2 f double prime k is equal to 0. So we have put it the value. Therefore in the Taylor expansion, if I use one more term order of h square, I get the Chebyshev method. Now as I said, the one of the roots only converges to the root. Which one is that, we will have to decide. To do that, what I do is I will retain this on the left hand side, this middle term on the left hand side, take these two terms to the right hand side. I have taken fk to the right hand side, minus half x minus x k square f double dash k to the right hand side, then divide by f prime k this. So I used this equation, the middle term on the left hand side, the other two on the right hand side, and written this particular thing which is still exact. Now I will define my next approximation as I put replace x by xk plus 1 this x by xk plus 1. So I write the next approximation as xk plus 1 here, xk plus 1 here, that is what xk plus 1 here, xk plus 1 here, that will give me the next approximation. Now it is still in xk plus 1, quadratic in xk plus 1. It is here I will now make an approximation wherein I will use here one of the approximations which is surely converging to the root. That means either a Newton-Raphson method or a secant method, I will insert it over here so that it will now become explicit. Left hand side is only xk plus 1, right hand side will be in terms of xk only. On the right hand side we approximate xk plus 1 this xk plus 1 by the Newton-Raphson method, that is xk plus 1 minus xk is minus fk by f prime k, that is our Newton-Raphson method. This I brought xk from the right hand side to the left hand side. So xk plus 1 minus xk is minus fk divided by f prime k. So I would like to replace this xk plus 1 minus xk by the Newton-Raphson method, which says that this can be approximated by minus fk by f prime k. If I do that, I will get xk plus 1 here, take this to the right hand side as xk, this term retained as it is fk upon f dash k minus half here, this is square of this, therefore I will have fk square, denominator is f prime k square, but there is also f prime k here, so f prime k whole cube into f double dash k. So this is how the computation, the Chebyshev method looks like, the computation for the Chebyshev method looks like. Obviously we are evaluating fk, f prime k, f double prime k. Now we would like to make a comment here that we have replaced it by the Newton-Raphson method. I made a remark earlier that Newton-Raphson method is of second order accurate. So I have used a second order accurate method here and then got this one. I will show later on that this method now becomes a third order method. That means the error at each step is now reduced by factor of whole cubed. So this is the next higher order than the Newton-Raphson method. But if I use in place of Newton-Raphson method a secant method or regular falsy, the order of the method falls down from 3 to 2. Therefore the method is of no use, because if it is only of order 2, I do not have to make it, it is going to be more expensive than Newton-Raphson method. Newton-Raphson method is of order 2, but here it is more expensive. Therefore if it gives me next higher order method, I will be willing to use one more function evaluation and then get the next higher order method, because the convergence number of iterations will be much less. Now if you use the secant or regular falsy method for approximation on the right hand side, the order of the method is reduced. Now to again count the computational cost, one evaluation each of f, f prime and f double prime. Therefore there are 3 evaluations that we are having here, and compared to Newton-Raphson method which has got 1 f and f prime, 2 evaluations. But since this is the order is 3, the total computation time that is taken for a problem would be less than even the Newton-Raphson method. The reason is that here the accuracy is third order, so therefore the error is reduced by power of 3. Therefore the accuracy that you would be getting will be much faster than what it would be in a secant method on this. Therefore even though at each iteration we are having 3 evaluations, but the total computational cost will be much less than what it would be for a secant method, and sometimes the most of the time the Newton-Raphson. Only thing is, if you say that I cannot evaluate f double dash in my problem, then we will not be able to use my Chebyshev method. I will have to take Newton-Raphson method, or I must find an alternative method to get the root. Now let us take a simple nice example. I want to find the approximate value of only simply 1 by 7 using 2 iterations of the Chebyshev method. Assume the initial approximation as x naught is equal to 0.1. Now to do a problem like this, I will first of all need to construct what is my fx. right. Only when I construct my fx is equal to 0 I would be able to construct what will be the value. Let x be equal to 1 by 7. Then I will invert it and write 1 by x is equal to 7. Then I will take my fx as 1 by x minus 7. So I would therefore define my fx as 1 by x minus 7. So it is necessary for us to, given a problem of this typical problem like this, to correctly write down what is my function x, so that any one of these methods can be used. Therefore I would write define as 1 upon x minus 7, and applying the Chebyshev method I need two derivatives. I differentiate this, f prime x is minus 1 upon x square, second derivative 2 upon x cubed. Now next remaining thing is simple computation. So I do with x naught is equal to 0.1, I find out what is f naught, that is 1 by 0.1, that is 10 minus 7, that is 3, f0 prime, that is 1 upon 10 to the power minus 2, that is minus 100, is 2 upon 10 to the power minus 3, that is 2000. So I just substitute this in the formula that we have written here, x0 minus f0 f prime 0 minus half f0 minus f0 prime whole square into second derivative by this. I compute this and get the value. Now I have to use this value and then compute my f prime and f double prime. So I need to, at each iteration I need to compute now these three values, this is f at this value, f prime at this value, and f double prime at this value, which I called as f1 prime and f1 double prime. Now these values shall now be used in the same formula, x2 is equal to x1 minus f1 by f1 prime minus half f1 by f1 prime square f1 prime by f1 prime. I will just retain this slide, this, yeah. No, I will bring it down, little bit down. Now you can see that I am writing x2 is x1 minus f1 by f1 prime, half of f1 by f1 prime whole square f1 double prime by f1 prime, and use these values and get 1 4 2 8 and 4, and the exact, now I can stop after 2 iterations, exact value turns out to be 1 4 2 8 5 7. We have got 5 plus accuracy in just 2 iterations. Of course we have started with an approximation as 0.1. If you take a different approximation maybe it would take one more iteration, but in 2-3 iterations it has given the exact value as this one. I think we shall stop it for today.